Okay. Hey, hey. So we want to chat a little bit because of all this information going around with the coronavirus, and we were like, well, what do we even know about viruses anyway, which isn't much. So I wanted to talk to the boys about it and see what they know about viruses. So my question is, can you tell us about like a virus and how it works? I know you've been doing your story, so you sort of know a little bit. So go ahead.
A virus is a type of thing that has to go into a cell inside your body to replicate itself, which it connects using these things on it, the little spiky things on the sides of it, to connect into the cell, and then moves its genetic code into the cell's genetic code, forcing the genetic code of the cell, and then multiplying the same type of genetic code from the virus, which then the cell has too many of them in it, and then it explodes with tons of new viruses in it.
Okay, so now how does the virus work? Because I was watching that other video that the guy posted, and he was saying how a virus isn't alive versus like a bacteria is alive. So a bacteria is like, somebody sneezes, somebody has a cold, and something sprays and gets on something, that bacteria is like alive.
Yeah, it is.
Now, that guy mentioned how like a virus doesn't work like that because it isn't actually alive. So what do you know about that?
Well, viruses aren't actually alive, except people argue about it all the time, not knowing. Except, I don't really know much about it, so.
You don't know much about the fact of viruses being alive or not alive?
Well, yeah, I don't really know.
So now, how does a virus work though, in terms of, is it just, is it its own thing, or does it need something else? Because I know in your story you mentioned how it's like he needs a partner. Like the virus needs a partner, so in your story you picked a bacteria.
No, that's not how it does.
Oh, so what?
But it just does it on its own, and it just attacks a cell, like it just explodes.
So a virus just attacks a cell out of nowhere.
Once it gets into the body, it finds a cell and then just sticks to it.
Okay, and how does it get into the body?
Usually through a vector or just through the air, like you breathe it in. Like you can breathe it in, it could land on a cup, it can land on your hands, which then you eat food with, it could land on anything.
So, what's a vector?
A vector is a type of thing that viruses travel through. Viruses are bacteria. So it's basically like a mosquito.
So a type of vector is like a mosquito would be a type of vector.
Yeah.
Okay.
Because the virus is inside the mosquito, then the mosquito bites you. When the mosquito bites you, it spits out some of its spit inside you too, which makes the virus go into you. Then you have the virus in your bloodstream.
Mm-hmm. And how does this can you compare it to another plague or something, how that worked? Like the type of vector that plague, the plague or...
So like yellow fever or what else? There's that one. Well, yellow fever spread through mosquitoes, and then the mosquitoes made eggs in the water, and then made more mosquitoes which had more virus in them, which then bit everybody, which made everybody have the virus.
Okay. And what about the plague? How did that work?
Oh, the Black Death?
Black Death, yeah.
So the Black Death is bacteria that started out somewhere and then got into a flea. The flea bit a rat. The rat had the plague inside of it. The rat dies. A flea bites the rat again, sees that it's dead, goes to another human, goes to another living thing, another rat or a human. Doesn't have to be a rat, it could be a squirrel or any rodent. And then it bites whatever it is, like a human. And then the Black Death goes in and it literally tears apart your cells. And that because it goes to the lymph nodes to multiply by just ripping themselves apart like this. Then there's more and more and more. Like 1 becomes 2, 2 becomes 4, 4 becomes 8, things like that. And then bumps form on your skin that swell and then bleed. And then it can go into your bloodstream and tear apart the red blood cells, which means less oxygen going to the body. It makes your fingers, ears, toes, and nose start rotting from the inside out. And then it could get into your lungs, which makes you cough all the time. And the liquid that comes out of the bumps could go on to someone else, which makes them have it. Or the cough could get on someone else.
Now, so the rats and fleas are vectors? Are those considered vectors?
Yes, except they can die from carrying them.
So the rats and the fleas can die from actually carrying it.
Yeah.
Why does that happen? Or
Well,
how does that happen? Them dying from it. They're not immune to it.
no, because the rat is just like a human. The same thing happens, really. And then the flea, they multiply inside of it, making it unable to eat. It doesn't actually get the plague, but there's too many of it inside of him that it makes him unable to eat and then dies.
Okay. So, and Theo, what's up with this? Why does it have a tail? This bacteria has a tail?
I don't know.
Why does it have a tail?
I don't know.
Nobody really knows. They just have it for some sort of reason.
Does the virus have a tail or?
No.
No, so the bacteria has a tail
Mhm.
only. So you can tell if it's a bacteria microscopically.
Sometimes it has a tail. Other times it might not.
Oh,
But
really?
most of the time it does.
Most of the time, okay. So, like, I was looking on, there's not really much information because I was like, all right, what's a vector? And TT was telling me what a vector was. And there's not really much. I looked on the American Society for Microbiology. Coronaviruses as vectors, stability of foreign gene expression. So this looks like October of 2005 abstract. So abstract, coronaviruses are enveloped positive stranded RNA viruses considered to be promising vectors for vaccine development. As genes can be deleted, resulting in attenuated viruses, their tropism can be modified by manipulation of their spike protein, and heterologous genes can be expressed by simply inserting them with appropriate coronaviral transcription signals into the genome. For any live vector, genetic stability is an essential requirement. However, little as is known about the genetic stability of recombinant coronaviruses expressing foreign genes. In this study, the Ranilla and the Firefly luciferase genes were systematically analyzed for their stability after insertion at various genomic positions in the Group 1 coronavirus feline infectious peritonitis virus and the Group 2 coronavirus mouse hepatitis virus. It appeared that two genes exhibit intrinsic differences, the Ranilla gene consistently being maintained more stably than the Firefly gene. This difference was not caused by genome size restrictions, by different effects of the encoded proteins, or by different consequences of the synthesis of the additional subgenomic mRNAs. The loss of expression of the Firefly Luciferase was found to result from various, often large deletions of the gene, probably due to RNA recombination. The extent of this process appeared to depend strongly on the coronaviral genomic background. The Luciferase gene being much more stable in the feline than in the mouse coronavirus genome. It also depended significantly on the particular genomic location at which the gene was inserted. The data indicate that foreign sequences were more stably maintained when replacing non-essential coronaviral genes. Many different viruses have been proposed as candidate vaccine vectors and are currently being developed into live immunization vectors. Ideal vaccine vectors are characterized by low cost, safe use, easy administration, induction of long-lasting protective immunity, adaptable targeting, and high physical and genetic stability. The recent development of efficient reverse genetic systems for coronaviruses now allows us to study the potential of these viruses as vectors. Previously, we have shown that the mouse hepatitis coronavirus, MHV, accepts insertions of foreign expression cassettes at many different positions. In the present study, the genetic stability of such coronavirus vectors is analyzed. Like I said, October 2005. This gets pretty wordy.
I have no idea what you all just
Yeah,
said.
I mean, it's microbiology. So, what do we really know? What are we really being told about what coronavirus is and how it functions and vaccine development? I don't know. Use your judgment, but I just wanted to share that with you guys because we were talking about it and I thought, well, let's just chat about it a little bit and then share it. That website, by the way, so that is, let's see if it'll load here.
I might want to write this down.
Well, it says that, oh God, I got corona.
No.
jvi.asm.org. I guess it's the website. It's not giving me on my iPad a specific URL. Just type in, I literally typed in vectors coronavirus. All right. Have a great day. See ya.